We talked a little bit about simultaneity when we talked about length contraction. Let's use the classic example. Okay, it's always box cars. It's always bolts of lightning. Striking and all this stuff, right? So here is point A1 and A2. Here, this is stationary. This guy's sitting still. Okay. This guy's moving at velocity v. Now, I hope you understand that this car is actually longer than it looks right now because it's moving by at a velocity v. And this could be quite fast, right? Sometimes it'll be like 0.85 the speed of light. If it was at rest, it would actually be much longer than this. But let's just suppose it's moving at some convenient velocity v such that that boxcar has the same length as this boxcar, right? Which actually is going to pertain right to the root of this problem, right? These boxcars really aren't the same length. This one appears to be the same length because it's moving past us at velocity v, right? Now, let's suppose these bolts of lightning strike, and they are simultaneous for observer 2. Okay, they are simultaneous for the stationary observer. Okay, the stationary observer knows that they're simultaneous. Here's how they know. They know that they're equidistant from A2 and B2. They know that the pulses of light from the event, they see it coming from A2 and B2, and the pulses arrive at the same time. And they also observe the pulses as traveling the speed of light, because of course light always travels the speed of light, regardless of the motion of the source or the observer. In this case, since it's simultaneous for this frame of reference, we see the pulses at the same time. They're traveling the speed of light. They had the same distance to travel, and therefore they happened at the same time. We can conclude nothing else but that. Now, observer 1 on the moving boxcar, okay, since it took some time for the light to travel from B1 to them, in that time they moved a little bit closer to B1, so they see the pulse in front of them as happening first, because of course they're going to, if these pulses are like here, right? Okay, maybe they're here and they're here. Okay, those pulses are, since you move into that pulse, right, you see that pulse first. Now, the weird thing is, and of course this is upon which it all hinges, right, is that you see that pulse of light not traveling at your speed plus the speed of light, but you see it traveling the speed of light. You see it coming from there. It's traveling only the speed of light. You see this one first. You see this one second. Therefore, this one really did happen first, and this one really did happen second in your frame of reference. Okay, things that are simultaneous in one frame of reference simply aren't simultaneous in the other frame of reference. You can prove that they're not at the same time, right? You see this pulse first, you see that pulse second. They're traveling the same speed, they have the same distance to travel. Therefore, this one actually happened first in this frame of reference. Now, I never understood that, so we can think of it in terms of length contraction. So yeah, there we go. Here's the argument there. Okay, let's just look at this, right? Let's suppose we have a car that is 14 feet long. It's moving fast enough so that it fits exactly inside a 10-foot tunnel, right? So we're sitting still. We're watching the car go by, right? So when it sits still, the car's 14 feet long, right? We just make the car move so fast that its length contracts to 10 feet, right? So then the question is, what is its speed? Question mark, right? Okay, well, that's actually pretty easy. Remember that the speeds are always c times the square root of 1 minus small squared over big squared. Right, so in this case it's c times the square root of 1 minus 10 squared over 14 squared. And I'm not even going to put the speed of light in there. I'm just going to go square root of 1 minus 10 squared divided by 14 squared, right parenthesis. And you get 0.69985, right? Or roughly, I'll say roughly 0.70 the speed of light, right? So there's its speed, right? Now, what does the driver see? What do we see? Let's talk about what we see, okay? We see the car fitting inside the tunnel. We see two different events. We see the bumper of the car leaving the tunnel, and we see that happen at exactly the same time that the rear bumper of the car enters the tunnel. The front bumper leaves, the rear bumper enters the tunnel at exactly the same time, right? Notice that we see the tires as not round anymore, right? They are actually contracted in this length, right? Okay, we see the car as thinner. We see the size of the tunnel as being 10 feet long, and the car is 10 feet long, right? And those events are simultaneous. The driver, of course, sees the tunnel. They don't actually see them moving. They see the tunnel actually is moving toward them, right? The tunnel is actually moving this way at 0.70 the speed of light. The car, the tires are round to the driver, and the car is 14 feet long to the driver. The tunnel is shorter, right? The tunnel is actually 10 times 10 14ths, right? The tunnel is actually shorter, according to the driver, right? They see the tunnel as, 10 times 10 divided by 14. They see the tunnel as being about 7.1 feet long, right? Their car is, of course, 14 feet long. This is what the driver sees, right? Okay, and of course the car doesn't contract with respect to the driver, because if it did, the driver would know they were moving, and there's no experiment you can do to tell that you're moving, right? So how long is the car? The car is 14 feet. The tunnel is about 7.1 feet, right? They see these two events. They see the front bumper leave first. They see the rear bumper enter the thing a distant second. Those two events are not simultaneous. And their tires are round, which is always good to know. Okay? You knew I'd get around to that.